Let's go ahead and introduce antiderivatives or integrals. We're going to be interchanging those names, but within a context, within the application. And a lot of times, so derivative gave us the slope of the graph, and then the antiderivative, we're always told, gives us the area under the curve. As you see in this picture that's given right here is the area under the curve. Now, a lot of times we're wondering, why is it the area under the curve? And some people might go years wondering that. I know people that, have been wondering that for years. And it actually makes quite a bit of sense. Why is it that when we take the antiderivative, we get the area under the curve? And then we're going to use that basically in this lesson. Really easy lesson, just to find the area under the curve. And that'll be the antiderivative, essentially, of the problem that we have here. So why is it the area under the curve? Let's talk about that. So let's just say we had a graph of the rate. And we know the rate is the derivative. So we'll say this is rate, this is time, and we know that distance equals rate times time. That's a classic thing. Think about it too. That always makes sense. It's a classic formula in math, but if you're driving, the rate is how fast you're going. So if you're driving 50 miles per hour for 2 hours, 50 times 2 is 100 miles that you, traveled. Right, if you drive 50 miles for 50 miles per hour for 3 hours, then it's 150 miles that you travel. So let's just say our rate is this graph right here. It's this horizontal line. And so we'll just say that was, our example, our rate was 50 miles per hour, right? And then depending upon our time, when time is 2, then 2 times 50 is 100. Well, guess what? 2 times 50 is the area formed by that rectangle, which would be 100. So you could see here that the area under the curve actually gives us the distance. So remember, the rate is the derivative of distance. The position, remember how it's position then velocity? The rate is our velocity here, 50 miles per hour. So if we take our velocity and we find the antiderivative of it, which is position, that would actually end up being the area under the curve, because we right here just did our base times the height to get the area of that rectangle. So obviously it's not going to always be that neat. It may be something like this. The rate is always changing, but basically if we find the area under the curve, that's going to be the antiderivative. It's going to give us that position, that total distance traveled in that sense. So another name we also give it is displacement. That's also another name. And that's going to be that change, that net change. And that's what this is about, exploring the accumulations of change. So that 100 miles actually represents your total change. That's 100 miles that you traveled, so you change from your starting point. So we also call this the net change as well. And displacement, forgot about that. Displacement is another name for it. So it takes 50 minutes for Joe to notice that his cola bottling machine has sprung a leak. Joe is able to stop the leak in 10 minutes. The graph below shows the rate. So this is a derivative graph. Pay attention to those kind of things when you're taking your tests, little details like that. So here the graph is the rate, the first derivative, at which Coca-Cola leaks from the machines as a function of time. It just says cola. They'd probably get sued if it was Coca-Cola, right? So how much cola does Joe lose in his bottling disaster? So if we have the rate that it's pouring out here, how do we find the total amount that he lost? How much left total? What's the net change here? How do we go back to that position function? And that would be essentially how do we take the antiderivative of this rate so we can find out how much was lost? So what that would be the area under the curve. Now, how would we find the area under the curve? I recommend that you section it off. Here's a triangle. Oops. And right here is another triangle. So we're just finding the area, like good old area math that we did back in I don't know what grade. So we have a 50 by 8. So 50 times 8, I believe, is 400, because 5 times 8 is 40. Add another 0 to it. And then here we have 2 times 50 is 100. Divide that by 2 is 50. And here we have 50 to 60 is 10 is the base. Times 8 is 80. Divide that by 2 is 40. Remember, 1/2 base times height is the area of a triangle is 1/2 base times height. Area of a rectangle is just base times height. So that's how I found those, right? So just add those up, 490. And that's going to be the antiderivative, basically. That's going to give us that net change. And we're obviously going to look more and more detailed to that. And you know, it's what is displacement? How is this the antiderivative? It's not just the antiderivative that we found. It's technically what we would call the from the fundamental theorem of calculus, a definite integral. And all these are different terms that we'll be going over in the future. But this is definitely something that you need to know. This thing, same idea. They're giving us velocity. They want to know how far did we travel. What's that net change? Break it down. Triangle, a triangle, rectangle. Find that area. Over here, this one looks a little bit more complicated, but you can see right there would be a triangle. Right here would be a triangle. And then last, right here would also be a triangle. So you just break it into the shapes that you do know and find the area under the curve, and that's going to be it for that assignment.